Hello viewers, in this session I will give you information regarding Clausius Clapeyron equation, which is very useful in the study of phase equilibrium. I will first introduce this equation to you. Clapeyron equation, I will give you the derivation and then how that equation can be extended to give Clausius Clapeyron equation, and derivation of that we will cover, and the application of Clausius Clapeyron equation, and finally I will summarize what has been discussed in today's session. Clapeyron equation. This equation was derived by Clapeyron from thermodynamic considerations in the 19th century. And this equation is applicable to one component, two phase systems. You have come across this terminology while studying phase equilibrium. This equation applies to equilibrium processes between any two phases, such as solid liquid in the melting process, liquid vapor during boiling, solid vapor sublimation, and then solid solid transition, as in the case of monoclinic and rhombic sulfur. This is the equation called Clapeyron equation. dP by dt is equal to delta H by T delta V. You are familiar with the terms involved in this equation. This equation gives us the slope of coexistence curve at the saturated vapor pressure P and temperature T. Let us do the derivation part of it. If two phases A and B of the same pure substance are in equilibrium with each other, and Ga and Gb are the respective molar Gibbs free energies, then the condition of equilibrium gives us Ga to be equal to Gb. If this were not the case, substance in the phase with higher molar free energy would pass into the phase with lower free energy, which is a non-equilibrium condition. Equal amounts of a given substance must have the same free energy in the two phases at equilibrium with each other. At equilibrium, dG is equal to 0. This is also the condition for the thermodynamically reversible change. So, dGA is equal to dGB. Since dG is equal to VdP minus SdT, we can equate the differential expressions for the two phases. We can write VA dP minus SA dt is equal to VB dP minus SB dt. We can rearrange it to give VA minus VB into dP is equal to SA minus SB into dt. Taking dt to the other side and rearranging the whole equation, we get dP by dt is equal to SA minus SB divided by VA minus VB into delta S by delta V. As we are dealing with the thermodynamically reversible process at constant pressure and temperature, we can write delta S equal to Qp by T, which can be written as delta S minus delta H by T, where delta H is the molar enthalpy of phase transition. Hence, we can write dP by dt is equal to delta H by T delta V. This is Clapeyron equation. Now, we can extend this to derive Clausius Clapeyron equation, which is dP by dt is equal to P into delta H divided by RT square. The Clausius Clapeyron equation is not exact, since approximations are used in the derivation. Its use is confined to processes involving vapor phase equilibrium, but nevertheless equation is found to be very useful. Let us try to derive it. Starting with Clapeyron equation, dP by dt is equal to delta H by T delta V. Use is made of the fact that for sublimation and vaporization processes, there is generally a large difference in molar volume between the two phases. In this case, delta V can be approximated as the molar volume of the vapor, and we can ignore the molar volume of the liquid. It is then assumed that the behavior of the vapor approximates that of an ideal gas, so that the molar volume V vap can be in turn replaced with RT by P, where P is the vapor pressure, giving us the equation dP by dt is equal to P delta H vap divided by RT square. So, this is the Clausius-Clapeyron equation, which approximates the slope of the liquid vapor coexistence curve at vapor pressure P and boiling point temperature T. Using the mathematical identity, we can write d ln P by dt is equal to 1 by P into dP by dt. The Clausius-Clapeyron equation can also be written in the form d ln P by dt is equal to delta H vap divided by RT square. If we further assume that delta H vapor is independent of temperature, integration of the above equation can be performed, and we can see here integration of d ln P within the limits P1 and P2 is equal to delta H vapor divided by R into integral 1 upon T square dt between the limits T1 and T2, so that we get ln P1 by P2 is equal to delta H vap by R into 1 upon T2 minus 1 upon T1. This is the integrated form of the Clausius-Clapeyron equation. It is possible to find out the enthalpy of vaporization delta H vapor if the boiling point of a liquid at two different vapor pressures is known. It is also possible for us to estimate the enthalpy of fusion, that is delta H fusion, if melting point of a solid at two different vapor pressures is known. And the third application is that it is possible to find out the change in boiling point of the liquid with pressure. If the vapor pressure P1 is known at boiling point temperature T1, the boiling point temperature T2 at another vapor pressure P2 can be easily estimated, but we must know the value of delta H vapor. Let me now summarize what we have seen today. I introduced you to Clapeyron equation first, because Clausius-Clapeyron equation is derived from Clapeyron equation. Then we derived Clapeyron equation. We extended the arguments to derive Clausius-Clapeyron equation from Clapeyron equation. The derivation is carried out, and finally we looked at some of the applications of Clausius-Clapeyron equation. And while studying the phase equilibrium, you will know the importance of Clausius-Clapeyron equation.